Welcome to The Explainer. I am absolutely thrilled you're here. Today, we're going on a visual journey, a deep dive, really, into the literal driving force of our civilization. We're talking about exactly how we power our planet. Let's get right into it. Okay, let's dive into this. Have you ever actually stopped to think about what truly powers the world around us? I mean, it's so easy to just flip a light switch, right? Or pump gas into your car without giving it a second thought. But the actual energy systems we rely on every single day, they are incredibly fascinating. And honestly, their origins might really surprise you. Now, to really understand energy, we first have to define what fuel actually is. And it's way more than just the gasoline in our cars or the coal in a power plant. Technically, fuel is any material capable of generating thermal power through combustion, fission, or fusion. So this covers a massive spectrum. We're talking traditional fossil fuels, byproduct fuels like blast furnace gas, chemical fuels like rocket hydrazine, nuclear fuels like thorium and uranium, and of course, renewable fuels. So here is our roadmap for today. We'll start by unearthing fossil fuels, then move on to refining crude oil. After that, we'll explore the carbon footprint pivot, take a look at the biomass alternative, and finally, we'll wrap up with managing biomass waste. All right, Section 1, Unearthing Fossil Fuels, a journey into deep Earth. You know, traditional fossil fuels are actually biological fossilization deposits. We're literally talking about microorganisms and plants that lived millions of years ago, completely transformed by intense heat and pressure over time. It's wild to think about. There are four major categories here. First, coal, which is our most abundant solid fuel. Then we have crude oil, that heavy hydrocarbon liquid we extract from deep wells. Right above that crude oil, we usually find natural gas. Natural gas is mostly methane, and it's widely considered the most environment-friendly of the fossil fuels because of its low emissions. And finally, we have oil shales and sands. These are very heavy oils, all mixed up with rocks and sand, which makes them super expensive to extract. Now, what's really interesting about this information is how different types of coal break down based on their fixed carbon and moisture content. You can basically see a clear geological timeline right in front of you. The general rule is, the older and deeper the coal, the higher the fixed carbon content. At the very top, anthracite has up to 98% fixed carbon. It's incredibly hard and burns with a smokeless flame. Next is bituminous, which is the most popular choice for power plants. As we go down the list to lignite, it gets younger, has less carbon, and honestly, it's almost wood-like. And at the very bottom, we have peat. Peat is essentially baby coal. It has massive moisture content. Though, fun fact, when it's dehydrated, peat is actually a highly effective absorbent for oil spills. Let's move to Section 2 and see how this builds. We're looking at refining crude oil, which is essentially sorting by temperature. Crude oil is an incredibly dense, complex mixture. If we break it down elementally, it's mostly carbon, somewhere between 84 and 87%, and about 11 to 16% hydrogen. You've probably heard the term sweet or sour crude on the news, right? Well, this simply refers to sulfur. It's sweet if it's low in sulfur, and sour if it's high. Naturally, sweet, light grades of crude are much easier and cheaper to process. But here's the catch. As those lighter oils deplete globally, we're increasingly forced to rely on heavy oils. And these heavy oils require really expensive, complex chemical methods, like catalytic cracking, just to break down those long, stubborn molecules into the useful fuels we actually need. So how do we actually separate that thick crude into these specific things we use every single day? The answer is fractional distillation. It's one of the oldest and most common refining methods out there. Basically, a single barrel of crude is heated up and separated entirely by its boiling temperature. It's like a giant sorting machine. At the very top, under 40 degrees Celsius, we get petroleum gases that we use for cooking. Turn the heat up a bit, and we get the gasoline for our cars. Hotter still, that gives us kerosene for jet engines. Then diesel, all the way down to temperatures over 600 degrees Celsius, where we get the solid residuals, that's the asphalt used to pave our roads. It is a remarkably efficient sorting mechanism. That brings us to Section 3, the carbon footprint pivot, the bridge between two worlds. To really grasp our environmental impact, we have to anchor our understanding in the global carbon cycle. Think of natural plant and microbial respiration as a continuous, balanced loop. Nature absorbs carbon, then releases it, perfectly balanced. But when we look at human emissions from things like factories, it's a completely different story. We're injecting entirely new carbon from deep underground directly into this atmospheric loop, and that severely disrupts that delicate natural balance. Now, this brings us to a really fascinating question. Most fossil fuels produce about 3 to 3.5 kilograms of CO2 per kilogram of fuel burned. Solid biomass produces slightly less, sure, but it still emits CO2 when burned. So why do fossil fuels cause global warming while biomass fuels do not? Well, it all comes down to the difference between positive and neutral carbon. Fossil fuels are positive carbon. They take carbon that was locked away underground for millions of years and add it to the active atmospheric cycle. Biomass, however, is neutral carbon. The plants we burn for biomass absorb that exact same carbon from the atmosphere just months or years prior. Burning it simply returns it. It creates a zero net balance over its life cycle. And this brilliantly illustrates why all emissions aren't created equal. When we look at the global warming potential, or GWP, carbon dioxide is set as the baseline with a value of 1. But take a look at methane, or CH4. Methane has a GWP of 25. This means it traps heat vastly more effectively than CO2. This is an absolutely critical piece of data to keep in mind as we evaluate any fuel source, because even a tiny release of methane has a disproportionate impact on our global temperatures. Moving on to Section 4, the biomass alternative, a nuanced solution.
Shifting to surface-level organic matter as fuel has some pretty incredible environmental benefits. First off, biomass is fully renewable, and it maintains that neutral effect on the global CO2 cycle we just talked about. But here's a lesser-known yet massive benefit: its impact on acid rain. Unlike traditional crude oil or coal, biomass contains virtually zero sulfur. That means zero sulfur dioxide emissions, which practically eliminates its contribution to acid rain. It's a huge win. However, to truly understand this topic, it is vital to look at the full picture. Biomass is definitely not without its serious environmental trade-offs. Remember methane's high global warming potential we discussed a minute ago? Well, microorganisms breaking down biomass in stagnant water reservoirs emit significant amounts of methane. Also, uncontrolled burning can cause severe carbon monoxide pollution. Additionally, if we continuously harvest crops for energy without letting the soil recover its minerals, we face severe land erosion. Even natural wood decay releases tannins, which is a liquid waste that can seep into the soil and pollute our groundwater. So, while it's a potent alternative, it absolutely requires intense, careful management to prevent deforestation and secondary pollution. Which brings us to our final topic, Section 5, managing biomass waste, energy hiding in plain sight. When we talk about biomass, we aren't just talking about chopping down fresh forests. We actually source a huge amount of this fuel from everyday waste. Biomass exists in 3 incredibly versatile physical states. We have solid waste, which includes things like timber offcuts, sawdust, and even the organic portions of your municipal garbage. Then there's liquid biomass, taking the form of bioethanol, biodiesel, and agricultural byproducts like cow dung slurry. And finally, gaseous biomass gives us valuable biogas and landfill gas, which is captured as organic material breaks down over time. The human ingenuity here really shines when you look at agricultural waste. Take oil palm processing, for example. Massive amounts of fiber and empty bunches are left over. We can burn rubber tree twigs and seeds, or the husks of coconuts, which actually make up 40% of the shell. We can even use the seed coats and prunings from the cocoa industry. Yes, the stuff used to make your chocolate, or the leftover bark from the timber industry. Things we traditionally consider literal trash are actually highly valuable, potent energy sources just waiting to be captured. Now, I want to draw your attention to a somewhat shocking category of biomass: hazardous biological and chemical waste. You see, biomass isn't just plant matter. Waste from research institutes and hospitals, and we're talking toxic chemicals, expired drugs, cancerous tissues, and yes, even human parts, are categorized as a viable form of biomass waste. While obviously highly hazardous and requiring extreme care and high-temperature incineration, it really highlights just how comprehensive the definition of combustible organic material really is. So, the crucial point is this: the future of how we power our planet isn't just about digging deeper into the Earth. It's about looking much closer at what we leave behind on the surface. Whether it's understanding the carbon footprint of an ancient fossil or the energetic potential of a discarded coconut shell, understanding our fuels is the absolute key to understanding our future. What waste did you generate today that could be powering tomorrow? Keep that in mind the next time you throw something away. Thanks for joining me on this explainer, and as always, keep learning.